warahmatullahi wabarakatuh. My name is Muhammad Azmi bin Kamaluddin. Today I would like to present my final year project, which is a dual mode antenna for sub-6 GHz communication. "5G is the fifth generation mobile network. 5G wireless technology is meant to deliver higher multi-gig per second peak data speeds, ultra-low latency, more reliability, massive network capacity, increased availability, and a more uniform user experience to more users. Sub-6 GHz communication is one of the frequency range for 5G application. Nowadays, 5th generation wireless communication is the new mainstream technology, which is an evolution of 4G LTE network. By using 5G communication, data can travel from one place to another with a very high speed transfer rate. To achieve 5G, the antenna needs high gain and broad bandwidth. For the problem statement, one of the antenna that have been studied produce very broad bandwidth, but the problem is it produce low gain, which is not suitable for 5G application. Next, one of the antenna has very high gain, but the structure are not low profile and not compact. The size is too big for the 5G application. Lastly, the antenna that have been studied has produced high bandwidth and gain, but the problem is it is very complex in design, which will cause the problem during the fabrication process, and it will take time to fabricate it. The main objective of this project is to design and develop low-profile antenna with a high gain and broad bandwidth for sub-6 GHz communication. Next is to study and validate the antenna design with the simulation software. Research scope and limitation. The antenna will design using the CST software. It will design for operational bandwidth of 3 to 5 GHz. The focus is on the S11 parameters, radiation pattern, and other parameters to observe the antenna performance. Model structure that have been designed will be studied in terms of parametric analysis. Theoretical review. Sub-6 GHz, also known as frequency range 1, covered frequency from 400 MHz to 7 GHz. Sub-6 GHz frequency are ideal for both rural and urban areas implementation. Ultra-wideband is the band which occupies greater than 500 MHz of bandwidth or greater than 20% of the operating frequency. Literature review. This is my state-of-the-art table. The first paper that I have studied is a simple wideband magno-electronic dipole antenna with a defected ground structure. It has very high gain and wide bandwidth, but the design is very complicated and hard to fabricate. Next is design of low-profile ultra-wideband antenna array based on planar dipole element. It has very high gain and very wide bandwidth. Furthermore, the design is simple and easy to fabricate. Another paper is a compact coplanar waveguide fed ultra-wideband antenna with a band notch characteristic. It has very high gain and wide bandwidth, and the design is simple and easy to fabricate. Methodology. The flow of the project are based on the flow chart. From the start of the beginning of this project, I need to determine antenna specifications. After that, antenna design calculation. Then the antenna is designed in the CST software. The CST simulation results are obtained and compared whether the result meet the specification or not. If the requirements are fulfilled, then the next step will be design parametric analysis, and report writing will be done for the last step. Vice versa, if the requirements are not fulfilled, then I need to design the antenna again, and the results are compared again whether it meets specification or not. This is the antenna specification. The frequency will cover 3 to 5 GHz. The substrate used is FR4 because it is cheap and easy to obtain. The gain is high, which is around 3 dBi. Efficiency is more than 50%. physical profile will be low profile, and the radiation pattern will be dual, which is omnidirectional and directional. This is calculation for the patch antenna for the preliminary design. The width of patch, the length of patch, and the effective dielectric constant have been calculated here. After patch antenna has been designed, notch ground has been added at left and right of the feed. This design has been inspired from several papers that have been studied. They use CPW antenna to produce high gain and wide bandwidth. Figure shown the parameter of the preliminary design. Several modifications has been made to the antenna to achieve the objective. The design of patch shape has been changed and the size of ground also be increased. In design 1 and 2, they produced omnidirectional radiation pattern for both low and high frequency. They also produce low bandwidth, which is below 40% bandwidth efficiency and has very low gain. For the design 3 and 4, the length of substrate and patch has been greatly increased. Tapered feed light has been used for both designs to enhance the bandwidth. Dual radiation pattern also can be produced by both of the design, which is omnidirectional and directional pattern. Both produce wide bandwidth and high gain, but design 4 bandwidth is higher than design 3. Design 4 has been selected as the finalized design. This is a final design after the modification process. The figures shown the parameter of the final design. Okay, next is result. Based on the S parameter result, the design antenna has an ultra-wideband performance where the operating frequency is from 740 MHz until 6.4 GHz, which is in the range of sub-6 GHz. Based on the result in the figure, the antenna produces a very wide bandwidth, which is 160% of bandwidth, and is suitable for current application. With this kind of result and performance, the antenna can be considered as good wideband antenna. Next is gain. Based on the result, we can see that the gain is vary between 2 to 5.4 dBi. It can be concluded that the antenna capable to transmit its signal at long distance. Antenna is dual mode in terms of radiation pattern. The radiation pattern is omnidirectional at the low frequency while directional at the higher frequency. In the dual band, the antenna is designed to have linear polarization and omnidirectional radiation for realizing a reliable wireless connection with base station and terminal around. In the high band, the antenna is for realizing a connection with satellite, and thus circular polarization and directional radiation are required. Figure shown radiation pattern of the antenna at low band and high band. Figure shown the E-plane and H-plane of the antenna at low and high frequency. The result shown the different width of patch size, which is 30, 36 and 38. At 3.3 GHz, the resonant frequency has shifted to the left when the width of the patch is increased from 30 to 38 mm. It also affects the return loss value where it decreased from negative 25 dB to approximately negative 16 dB when the width of the patch is increased. The result shown the antenna with different length of patch, which is 70, 80 and 90 mm. At 2 GHz, the return loss is increased when the length is decreased from 90 to 80 mm, but when it further decreased to 70 mm, the return loss decreased. At impedance bandwidth of 1.2 GHz to 2.3 GHz, the frequency slightly shifts to the right. At 7 GHz, the return loss decreases when the length is changed from 90 to 80 mm. However, return loss increases when its size further decreases to 70 mm. Hence, it is realized that the best length for the antenna is at 90 mm. In this analysis, the width of substrate has been increased from 40 to 42 and 44 mm. As the width is decreased from 44 to 40 mm, the return loss at 7 GHz is improved from -30 to -42 dB. Based on this result, the best size for the antenna substrate is at 40 mm. The length of the substrate has been increased from 140 to 160 and 180 mm. As shown in the result, there is no distinct change that can be observed from the result, although the size has been increased to a very high value, which is 180 mm. The length of X has been adjusted to analyze the result. Based on the result, at 7 GHz, the change of length has improved the return loss value from -16 dB when X is 8 mm to -42 dB when X is reduced to 2 mm. When the size of X is 2 mm, it produces better result than 4 mm and 8 mm, as it also produces higher gain, which is good to transmit signal to further distance. The tapered feed upper and lower width has been increased to analyze which can produce the better result. When the width of the feed is decreased, the return loss at 7 GHz is improved from -13 to -38 dB, where the upper and lower width is 0.35 and 1.8 mm. It can be concluded that the lowest width used has better impedance matching. Dual mode antenna for sub-6 GHz has successfully been designed and presented. The antenna has operating range of 740 MHz until 6.4 GHz with bandwidth efficiency of 160%, which is very wide. The antenna also produces high gain between 2 to 5.4 dBi. In this project, the antenna is dual mode in terms of radiation pattern. The radiation pattern is omnidirectional at the low frequency band, while directional in higher frequency band. The antenna has achieved the specification and requirement in terms of operating frequency, bandwidth, gain, and radiation pattern. Parametric analysis of the antenna also has been done in order to understand the behavior of the antenna parameter. Finally, for the recommendation, first is to improve the miniaturization of the antenna size in order to make it more compact and suitable for mobile application. Next, improve the radiation pattern of the antenna where to keep it sustained to be omnidirectional throughout the frequency. It is also encouraged to add a notch band to reject certain frequency range.